on neuroimage and connectivity and mental health. In this case, it's the second day also for the satellite seminar of Institute University of Neuroscience in University of La Laguna. I would like to thank you to Professor Nico Macris for the organization of this winter school and offer us the opportunity to listen experts in neuroimage around the world, and also to show our research to these people around the world, because the neuroimage and connectivity and mental health is also in line with the goals of our institute. So we are proud also to show in this seminar our force, our muscle, with 4 of our best researchers, which are, in this case, in first place, Niels Jansen, who is investigating in the hippocampal subfields with resting state fMRI. He started in this ground after his PhD in Harvard with Alfonso Caramazza. In this time, he worked about naming of words, about language, with recording of ERPs. And now is interested in this other more anatomical and related to illness in cerebral illness in Alzheimer's, Parkinson, and some other cerebral disease. And he's a very, very expert in the refining of these technical aspects of fMRI. So after Niels Jansen, we have a talk presented by Manuel de Vera and Francesca Vitale. Manolo is our emeritus professor here in La Laguna after more than 40 years of research in different fields of research, mainly centered on language, and now very interested in the research about the representation and embodiment of language, and using very, very innovative technical aspects related to TMS and TDCS. Francesca is a postdoctoral student from Italy, and she works also with Manolo, and she obtained here in La Laguna her PhD with under supervision of Manolo de Vera. They will offer a talk about TMS and TDCS as tools for functional brain analysis. Then Hipólito Marrero, Damián Hahn, and Agustina Birba. Hipólito Marrero is also our professor, an expert in emotion and motivation, and he is now very interested in the cerebral mechanism of the cerebral representation of avoiding and attracting behavior and social cognition, neurosocial cognition, and this representation in the brain. Damián and Agustina Birba are postdoctoral fellow researchers in the institute also, and all of them will talk about Neurocognitive Toolbox. It's an instrument to evaluation of different mental disorders related to this mechanism of avoiding of attracting behaviors called neurococtul, sorry. And finally, Ernesto Pereda is our engineer expert, very expert in EEG and analysis of different recordings of several signal, in this case electrical and also magnetic signals. And he is now investigating about the connectivity, the possibilities of EEG to offer data about the connectivity of different areas in the brain. So the talk of Ernesto will be MEG connectivity in the study of Alzheimer's disease, pros, challenge, and the way forward. So without another talk, without another words, we start with Niels Jansen to offer this conference. You want?
Yeah, I can.
Yeah. Better. Si tienes, se tiene puntero.
Bueno,
por ahí, ahora paso las diapositivas, era para ajustar la cámara solamente.
Okay. All right, so thank you very much for inviting me. So I'll speak in English. Yeah, so I'll just get started. So I'm going to talk a little bit about some research that I'm doing. It's a slightly different title. So it's, in addition to just having resting state, also discuss some task fMRI stuff. Basically because the talk was longer than Alberto told me in the beginning. So I'm talking about the hippocampus. So hippocampus is one of the most studied regions in the brain. Why is that? Well, it's a region that is involved in many different diseases. So it's involved in things like stress and aging and Alzheimer's disease, epilepsy. There's also a lot of cognitive functions that this region is involved in, like memory, maybe even involved in language. So I mean, it even has its own journal, right? So it's a really a region that is very popular in neuroscience. And so just to make sure everybody knows what we're talking about, so a little bit of neuroanatomy. So the hippocampus is a structure that if you look at the medial part of the brain, it's sort of in the middle, a bit behind the temporal lobe. Here the hippocampus is in green. Perihippocampal gyrus, entorhinal cortex in red, and you can see this is a pretty large structure. It's about 5 centimeters. So in human brain, in actual section, an actual fixed brain, hippocampus is a very funny looking structure. I think actually that's the real reason why many neuroscientists are interested in the hippocampus, because imagine you are dissecting the brain and you see something like this, and you're like, what is this? So it's a funny looking structure, and yeah, so lots of work has been done on this stuff. So in my case, and this is also not only my idea, but to understand what the hippocampus is doing, we have to look at the connectivity. So we have to understand how the hippocampus is connected to other parts of the brain, and in that way, we can sort of understand a little bit more of what this structure is doing. So in my case, I'm going to be talking about functional connectivity. So with fMRI, in this talk, it's not too technical. So I'm assuming you know a little bit about what is functional connectivity. So you have structural connectivity. That means that actually two regions are really connected with each other, like they're actually connected through axons and white matter connections. Functional connectivity means that two regions are functionally involved in having the same function. And this might be found out, you might discover this by looking at time courses or this kind of analysis. So it's a connectivity that is different from structural connectivity. So functional connectivity for the hippocampus is not so easy, and to make things more complicated, the hippocampus actually is not a homogeneous region. No, it's not one solid mass of cells. Actually, there are inside the hippocampus a lot of different areas that have different connectivity profiles and that have different cells. They have different types of genes, different molecular properties. So there are differences between different parts of the hippocampus. No? So it's a complicated structure that has an internal structure that it looks like it's doing different things. So like things like the CA1 field, the substituent field, they're all parts of the internal structure of the hippocampus. And so given the small size of these subfields, so we're talking about maybe a millimeter. So this, on average, the size of these subfields is around 1 millimeter. Doing functional imaging is kind of challenging because they're small. So you need to have, on the one hand, fMRI sequences on the machine that are not standard, right? A standard sequence gets fMRI data at around 3 or 4 millimeter resolution. And given that these subfields are around 1 millimeter, this doesn't work. So you need to do something that is not really standard. At the same time, you need good methods for segmenting these subfields. And there are methods, automatic methods or manual methods that do that. But you also need good images to be able to do that. I mean, this is all based on MRI. We're not doing any histology or actual brain stuff. So everything comes from the machine. And we need to have good images to be able to segment these hippocampus subfields. Registration is also important. So if you get your data in a structural scan and you do your segmentation in a structural scan, and you want to then look at fMRI data to see something about the activation in the hippocampus, you have two different types of images that you need to register to each other, which is not simple, especially if you have to have high resolution fMRI, which means maybe you need to have a partial volume acquisition, not the whole brain, all kinds of complicated things. The analysis techniques may not be standard as well because you're dealing with maybe areas that have low signal to noise. It's a complicated thing. But for me, actually, it's what it makes it interesting, right? These kinds of challenges. I mean, I don't know. Maybe maybe I'm a computer scientist and I like this kind of stuff. So this is why I think that it's fine, right? And it makes it fun. So basically, I'm going to talk about two different studies. One doing subfield functional connectivity using resting state fMRI. So this is a data set that is available on the web. So it's a 7 Tesla Unimectome project data set. And then the other study I will talk about is a study that we collected data here in Tenerife, but with a task. So it's a task-based fMRI study. So there's these two studies. So resting state fMRI. So one of the major discoveries in the past couple of decades, actually very important discoveries that have been done with fMRI is that the discovery of these resting state networks. So when you put somebody in the scanner and you do an fMRI scan and they don't have to do anything, they're just lying in the scanner, different parts of the brain become activated. And the funny thing is that this is not random, that it doesn't happen differently in different persons, but it's really consistent between people. So there's really a number of patterns that we call these resting state networks that really robustly replicate in different people, different populations, and these are these resting state networks, right? So something like the default mode network is an area of the brain that has a very typical, prototypical pattern of a number of regions that are activated when people are at rest, right? When you're not doing anything. There are different networks, but there's a discussion about how many networks there are, but these are some of them. And so that's well known. It's also well known that the hippocampus is a part of this default mode network. So when this default mode network is activated, you also have activity in the hippocampus. So those things are well known. So there's two major issues that are really not really well understood at this moment. And that is whether, the first issue is whether the hippocampus, besides the default mode network, is also activated in other resting state networks. So it's, the default mode network becomes activated and the hippocampus also, but there are other networks and we don't know what role the hippocampus plays in those. And the other question that is more the focus here is about these subfields. Obviously, the hippocampus has internal structure, and we have really no idea at this moment how these other subfields are connected with these resting state networks. What are they doing? And you have a default mode whether which of these subfields is primarily activated in the default mode network or in other networks. Right, so the internal hippocampus, there's a missing image here. So I was supposed to show here an image of how we actually segment the hippocampus, but I don't know why it's not there. But, so there's this is an actual histology, right, of an actual brain. But with fMRI or with MRI, we get high-resolution structural images that we automatically analyze using the fixed surface software, and that allows you to detect these individual subfields. That procedure, well, I can go into details, but it's kind of it has a template of what it should look like, the different subfields and the way that they are positioned, and then it fits that template onto the actual brain of a person and takes into account all kinds of other landmarks so that it's positioned in what they have determined in the optimal way, right? So they have done some tests that is the optimal way to position these. But of course, it's not histology, it's just MRI, right? So we're not 100% sure that this is the correct segmentation. Yeah, it's too bad this was not there. So there are some theories about hippocampal connectivity that exist already. This is a paper from Nature Neuroscience, Nature Reviews Neuroscience, famous paper from 2012. And so here you can see that that in blue, sort of the posterior part of the hippocampus, so that the posterior part is towards that side, so the back side of the brain, is connected to things in the posterior part of the brain. So, right, so the posterior part of the hippocampus connects with areas that are in the posterior side of the brain, makes sense. And the anterior part of the hippocampus connects to parts that are in the anterior part of the brain. So what they're saying here is that that this posterior system is actually the default mode network. So the posterior part of the hippocampus, according to this theory, connects with the deep neural network. And then the more anterior part, it's not really known. So the anterior part connects to a bunch of different areas. They don't know which resting state network that is. It's not being identified. There's things missing there. So we wanted to basically look at how this connectivity was established in a So we did this resting state study to look at hippocampal connectivity. This is a human connectome 7 Tesla data set. So that is a data set of around 180 people actually, but with some quality control. We had to go down to 172. They're all healthy young adults, so they're all lower than 35 years old. And it's 1 hour of resting state fMRI. Right, so that's crazy. 1 hour of just resting in the scanner. That's a lot of data. So and it's 1.6 millimeter cubed. So there's supposed to be a truth. So it's isotropic. So every voxel measures 1.6 millimeter in all 3 dimensions, and it's a whole brain scan. Right? So that I think in terms of quality data, probably the best quality data that you can get on the with high resolution, whole brain, the PR is very good, so it's really high quality data, and there's a lot of it. So the kind of analysis we did, functional connectivity analysis, were independent component analysis. So I'm not going to go in a lot of detail what we did exactly, but we did basically independent component analysis, which is an analysis that you can think of as a kind of clustering technique, where it will detect voxels that have similar time courses and group them together. It clusters voxels that have the same property in time, right? So when they vary in time in the same way, it puts them in a group. So that is, in a sense, a functional connectivity analysis. Then that has to be done at the group level, and so that means that everybody has to be put in a standard space. No, this gets a bit technical, but this has to do with things like the registration problem and collecting fMRI data in a different space than your structural data. So actually, all the analysis we do in the native space. We don't transform as little as possible the fMRI data. Do some motion correction, but we leave the fMRI data as it is, so we don't transform it in any way. The only thing we do is for each subject where we have the hippocampal segmentation, in that subject's T1 native space image, we transform it to the fMRI space. That's the only thing we do. That's the only transformation we do. And that's, I think, unavoidable at this moment. But so it's important because these hippocampal subfields are so small. If you start transforming the fMRI data, you might blur voxels from one subfield into another subfield, and your analyses come on. We also did some additional types of statistics that I also linear mixed effect modeling is the type of regression modeling we do. Wow. Where are the images? Before they were there. There are no results. The whole paper was just this little table. No. No.
Could you, so
And
there
then-
are,
And you, and then,
El archivo puedes abrirlo con LibreOffice. Yeah.
vale. Okay, so, so in the resting state study, we found basically that the hippocampus had two clusters of activity. There were two clusters of activity inside the hippocampus. One that was more in the posterior position. So this is a view of the hippocampus again. So the middle part of the brain, the hippocampus is here. And you can see that there's a posterior section of the hippocampus that is colored in green. So that is a separate cluster from the area that's colored in red. There were two clusters of activity. This hippocampal cluster was connected to the default mode network. So that is the posterior part of the hippocampus. And there was another network that was the somatomotor network. So the hippocampus connected to two different networks. One was the somatomotor network and one was the default mode network. Okay, so we did analysis where we correlated maps with a bunch of resting state networks, with reference resting state networks. And basically, these two networks were most highly correlated with our data. So that's the whole brain connectivity. If we look at the actual subfields of the hippocampus, so we find that in the default mode network, it is mostly the subiculum that is activated. So it's mostly the subiculum inside the default mode network, and in this other network, the somatomotor network, it's mostly CA1 and CA3. So this is good because this is showing us that with our technique, we are able to at least separate different subfields, right? So we're at least getting different results from different subfields. I mean, if the data was not good and if our analysis was not good, maybe it would be just activated all over the place. But the fact that we can differentiate different subfields, that's good. Basically, posterior hippocampus connects with the default mode network, anterior part is somatomotor network. So that's new. Previously, that was not known. And then C1, C3 are especially relevant in the somatomotor network and subiculum in the default mode network. Why we get this difference in the paper, we speculate a bit about that maybe C1 and C3 are regions that are more involved in sensory motor processing. They're more involved in information that's coming from outside. And there's some evidence for that as well. And subiculum may be more related to self-referential, maybe endogenous processing. But of course, getting functions from for these subfields from resting state data is really complicated. I mean, resting state is just people are not doing anything. So figuring out the function of regions is not easy. So we then try to do the same thing, but using a task. So there's subfield. There's not that many studies that have looked at subfields with tasks. But some studies, recent studies, have suggested that actually subicular complex is very activated when you ask people to do autobiographical memory tasks. You know, if you ask them to remember the birthday of your best friend 1 year ago, and in that case, you get activity in the subiculum. The problem is that with those tasks, that they're very hard to do. And to ask people, some people are really good at these tasks, some people are really bad at these tasks, so you have to kind of select people. The task itself is also complicated because when you ask people to remember the birthday, the moment in time when they actually remember this, it might take 10 seconds, it might take 5 seconds. So linking that to a stimulus it's not obvious. And in fMRI analysis, you need to know when things are presented, right? So the tasks are kind of complicated. So this is work that I'm doing with somebody that is actually an expert in these kind of tasks. So Marshall Dalton is a researcher in Sydney that is where we're doing this with. So we come up with a different task in which it's actually a sentence reading task. So people read a little story in the scanner, and the idea is that this is also involved in generating a memory or a construction of a scene that is much easier to control, because with this task you're presenting the stimuli, people are reading it and they are imagining what's going on. Maybe they're imagining that it's something that happened to them also. So in this task, it's a very simple block task, fMRI block design. So it's not 25 seconds of stimulus, then off, 25 seconds of stimulus, off. That is done. We did the experiment here with people from students from the university. So it's here the GE machine we have before. It's not the new one, but it's the old 3T scanner. We managed to get 1.5 millimeter cube, like in plane resolution, with a pretty good DR. We did T1 and T2. The T2 was really high resolution, so that helps with the segmentation of the subfields. Pre-processing was done using HCP pipeline, and then automatic segmentation using FreeSurfer. So these are the results. Looking at this with a sort of, it's a thing that I usually do, looking at fMRI data with tasks, so to get a kind of dynamic view of what's actually happening in the brain, right? So this is this 40-second block. So there's when we're reading the sentences, and then sort of the average of all the trials and all the subjects, right? So it's everybody, grand average analysis, like they do in BG, then fMRI. And so you can see that so the left side of the brain is much more activated than the right side of the brain, which is something that is typically found in sentence reading. So it's a sentence reading network, that is more, looks like temporal and frontal, so it's typical sentence reading. But you can also see here that hippocampus is extremely activated. So this is a complicated, temporally dynamic form of the data, and then what we usually do is again to do ICA and to try to group together those voxels that have a similar time course. And so then what you get is that you get a kind of temporal profile of what's happening in this block, and you also get a map of the activity. So you can use both of these types of information to say that these voxels are in the task, they're related to the task. And other voxels that are at other positions and that have a different temporal profile, they are not related to the task. They may be noise, or they may be in fact be related to default mode network activity during the task, because that's something that also has an fMRI, is that when you're doing a task, your task regions go up in activity, but the non-task regions, they go down. So the default mode activity decreases, and that's what you see here. There's a decrease in areas that are kind of typical default mode. The other regions that is detected by ICA is most likely noise. This is just activity and ventricles that we don't care about. It's just ventricular activity. But this is a nice, I like this to separate out those parts of the brain that are doing the task, right? And the other things we can just ignore. Also with ICA, you also always have a problem of you have to choose the number of dimensions, you have to say how many you choose, and then we sort of try it with other dimensions and get the same thing. So then we do statistics, and we look at actually with with subject level statistics. Again, everything is done in native space. We don't try to transform as little as possible because we care about precision. And we basically get a pattern in the whole brain that this looks like a typical sentence reading pattern, that the left hemisphere is more activated than the right hemisphere, like blue and yellow. Blue is bigger than yellow, and the regions, they are ranked by how much activity there was, right? So the top ones are the most activated: superior temporal, middle temporal. This is left broca. So it's a typical sentence reading, but hippocampus is really activated in the past. And within the hippocampus, if we look at the subfields, then you see that in the body of the hippocampus, actually the subiculum, the presubicum, is one of the most activated regions. So that was in line with our predictions. This actually more or less this area here. Okay, so in this study, which is a task fMRI study, we found left lateral large network that's typical of sentence reading. We found that the hippocampus was really strongly activated in this task, and that actually the inside the hippocampus was related to CA3 and presubicum. And we interpret that as consistent with these ideas of what you're doing in this task is constructing a scene. You're imagining what is happening to these people. And so in the future, this is interesting because it's a very flexible task. I think, it's probably easy to do also with older people, clinical people. Okay, so just to wrap it up, I think it's technically challenging to do a hippocampal subfield. It's not easy, but it's possible. So we need to do some non-standard things, but it's possible to do. So in the future studies, I like to play around with this task, this sentence reading task, and apply it maybe to clinical populations. I have a project that is about to start looking at Alzheimer and older people. Also, in the same project, relating this to things like sleep and physical activity, which also gets to Alzheimer therapies and things like that. I think this is interesting. It's also part of this project, and so we're starting with getting around 120 students with these Fitbits, tracking their sleep, tracking physical activity, and then using scanner. So that's it. So I'll thank my people from my lab. my collaborators, and thank you for your attention.
Any questions? There is
I have a question.
Oh, yeah.
So thank you very much. Because we're seeing a significant group, would this work with a single subject approach? Because I see you are interested in maybe going into application, Cyber's application. So sometimes we are able to see things at the group level that we can't see at the single subject in most of the subjects. And in relation to that, in the video you showed us, which is beautiful, would you specify the threshold level that you were setting so that we could see this?
Sure. Yeah, so I mean, the question about individual subjects, I mean, the fMRI is notoriously noisy, right? And people are working on trying to reduce noise in fMRI. And there's all kinds of new techniques looking at thermal noise, trying to reduce thermal noise. My personal experience is that in single subjects, we get pretty good data. It depends on also the quality of your fMRI scans. That's not straightforward. It's always a trade-off between resolution and the coverage and the TR. Those things are all linked to each other. Whole brain, if you want a whole brain, you need to maybe reduce the signal to noise by increasing what's called multi-band factor, which is not a simple thing.
So you could have gone for a multi-band and reduced TR maybe underneath the setting.
In our data, and the one that was collected here at the time, this was not possible because this was with an old MRI machine that we had. I think now maybe it's not possible.
Yeah, with G you can.
Yeah. But we had it was a software version of the machine that did it. But we could do this now. And something, but I mean, it's not like you can just increase the multiband factor and everything is fine. No, because when the more higher the multiband factor, okay, you reduce your TR, but you also lose signal to noise.
And also from a cognitive point of view, maybe you if you reduce TR, you lose a chance of sampling the moment, the cognitive processing where that something is happening, or
I don't know. I mean, TR. Well, that's also a discussion. And the TR around 2 seconds seems to be a pretty gold standard, and enough for most studies. I mean, there are people doing TRs of sub-second. The benefits are, in my opinion, not that obvious.
no? But you do slice timing correction.
Yeah, I do, but this technique that I do is not necessary to do slice time correction. Because, I mean, it's a slice-based technique, and it shuffles the slices in a way that it takes into account exactly when each slice will apply. Well, yeah, there's also a longer technical discussion, but it doesn't require slice correction.
one other question.
A very quick one, and nobody else has one for the sake of time. We can go almost afterwards if short as of time. This thing of anti-correlation, how do you associate that, or is it possible to associate models with inhibition or excitation?
With what?
Inhibition or excitation in the network?
Yeah, I don't think so. I mean,
Let's stop there, it's a long question.
This is a big.
I just wanted to know if you had an idea.
Yeah, no, I think this is a big topic, and that's interesting.
Absolutely.
Okay, thank you very much. And the next talk is PMS and PDCS as tools for functional brain analysis, Manuel Francisco Vidal.
Igual hay menos luz para o mejor de aquí.
Can we start? So, first of all, thank you, Nikos Makris, for organizing this wonderful winter school, which allows us to attend talks by outstanding researchers all over the world. And also very important, this year, we also have the opportunity to present our own research in this framework. Just a small remark about the framework you established for this session. In your long introduction, you say several things, and one of them caught my attention is that we should align our background and cultural approach to the big universities and centers of the world in terms of ambition and fire research and things like that. Okay, I just want to be a little in disagreement with this recommendation because to some extent we already are online, so we are on the track. Our center is modest, is small. We are in a university which is not top-level university, but I can say that we are resilient in many ways. If you look at our production, our publications, you will realize that we publish in international journals like Cerebral Cortex, the Journal of New Image, the Journal of Neuroscience, and many others. So this means that we are not so provincial, probably, as you think. And in addition to that, the cultural environment we're immersed in is very ambitious. We have a policy of recruiting talented people, young researchers. We have an international networking, and our production aspect is very good for this modest environment. And this is in spite of the university. So the university is not optimal, it's suboptimal in many respects. Everything is much more difficult in this university than in others. And in spite of the many obstacles, institutional obstacles we have, we managed to do things pretty well. And we keep intact ambition, the need to connect with other people. We have young people very ambitious with their research, that the training, sophisticated protocols, and so on. So, just an example, I think that this talk is a beautiful example that we are able to do this international level research. Today, I want to talk about the research we do using non-invasive stimulation, brain stimulation techniques for mapping brain functions. So let's focus on the research in the framework of embodied cognition. So many of us are devoted to the understanding, to investigating the language comprehension, and our approach has to do with the theoretical background of embodied cognition. Embodied cognition means that in addition to the ordinary brain areas devoted to language, like Broca or Webber, we think, and many other people think, that other brain areas are involved, which are more sensory motor. For instance, when we understand action-related language that involves verbs, action verbs like throwing, grasping, and things like that, there are plenty of evidence that the motor and premotor areas of the brain are activated. And this has been demonstrated by means of EEG, MEG, and neuroimaging techniques, especially fMRI. All these techniques are extremely useful because they provide information about the dynamics of the brain, in the case of EEG and MEG, and a high-resolution temporal approach to the brain signals. And on the other hand, the fMRI techniques and similar provide high-resolution spatial view of the brain. All these techniques are extremely useful and make a great advance in our knowledge of language functions, but they are basically correlational. So they don't demonstrate that there is a functional or causal connection between the brain areas that are activated and the function, the linguistic function we are analyzing. So there are other procedures to overcome this lack of causality approach. And one of them is, well, studying brain patients is one of them, of course. These people who have some damage in their brain suffer some specific impairment in their linguistic behavior, in their performance. And the other kind of technique has to do with non-invasive brain stimulation, not for therapy, but for mapping functions. So the approach has to do with trying to map functions, linguistic functions in our case. So these are a short list of some of the experiments the research we perform in our laboratory, most of them with Francesca Vitali and other people. All of them are related to the main issue of embodied cognition, language. And well, the first point has to do with the understanding the functional role of the motor cortex in action language. And in this line, we ran some experiments with RTMS, one of them, and with TDCS in another case, stimulating and enhancing the excitability of the motor cortex, and then analyzed the consequences of language comprehension. And the consequences were very specific. So when these areas were stimulated with excitatory stimulation, another TDCS, for instance, the comprehension of action language improved, and even more, the long-term memory improved. So the free recall of the action sentences was better after stimulating with analog TDCS. And this was very specific. So this didn't happen with non-action language related to other verbs like visual verbs or abstract verbs. The second line of research has to do with inhibition. We are very, very focused on the role of inhibitory processes in many things, but one of them is language. In language, we claim that inhibitory processes and excitatory processes are involved in a fine balance between them. And our demonstration has to do with negation, negative language. So the negation is a very common linguistic tool in all languages. And what we are looking for is exploring how inhibitory mechanisms of the brain are operating, are recruiting while people understand or produce negations. And for this reason, one representative study involved the inhibitory stimulation of the right inferior frontal gyrus, which is known as a main inhibitory web or hub in the brain. And when people receive the inhibitory low frequency inhibitory stimulation in this area, the negation processing was altered, was modified. So basically, the brain response to negation was exactly the same as in affirmative sentences after producing the activity of the inhibitory network. Another line of research has to do with per pulse TMS, which is a protocol that was used to analyze the activity of the GABAergic system or the glutamatergic system, depending on the particular timing of the stimulation. And when we stimulated short intracortical inhibition, about 5 milliseconds between the pulses, this it is well known that this has to do with a modulation, a specific modulation of the GABAergic system. And we observed that this CT stimulation on the motor system modified the comprehension of negative sentences. So we have some evidence that negative sentences also reuse the GABAergic system. And finally, well, almost finally, we also are using these co-registering protocols of TMS EEG, by which the production of a single pulse in a given target region allows to track the flow of information. In this case, information is induced by the electrical pulse, and the EEG provides a moment-to-moment evolution of the current, the electric current displayed by the TMS, and this allows to explore connectivity, functional connectivity. In our case, we were interested in how the functional connectivity between the motor cortex and the ATL, the anterior temporal lobe occurs. Why these two regions? Because the anterior temporal lobe is to tell that there is a main semantic hub. Many people say, okay, all that has to do with meaning, with semantics, occurs in the anterior temporal lobe. And the other activations that you can register, like motor cortex or visual cortex or whatever, are irrelevant, are epiphenomena. So what we do is stimulating ATL or M1 and explore the course of the flow of information. And we discovered this is a very new study that we have all the analysis done, but it's not yet published. This study is very informative because we observed that the flow of information from M1 to the ATL was in this direction. So when people understand action language, first M1 is the critical region, and then the information goes to the hub, to the semantic hub. And this is in conflict with other people say. Other people say, no, first is the semantic hub, and then there is a cascade effect to other regions. Okay, so the last point is, well, I don't want to talk about that right now because this is the point that Francesca is going to develop. Francesca.
Okay. Here is we present the list of our publications that Manolo has just presented to you, our works. This one are in preparation, this one is already submitted, but this one is, we are writing it, and I'm pretty happy about the last one because it was really hard to apply the TMS-AG with a really innovative protocol to something complex like language. This I want to underline the complexity of some physiological techniques applied to a non-cognitive process. But today, I'm not going to present that. I'm going to present another study that has a more social meaning. Let's say like this. It is already published, and I'm going to present it to you. Okay. Social exclusion or rejection can induce feeling of social pain. Okay, like when I say I don't like you, it will provoke to you something pain, but not a physical pain, something social. So we call it social pain. And it was demonstrated that the social pain is processed by the same area, but by the same brain regions that are involved during the process of physical pain. Okay, there is an overlap. And until now, all the studies that investigated the social exclusion only use some paradigms like the cyberball task, which are tasks that simulate a situation of social exclusion. These studies didn't consider at all the possibility of using language, but like the example that I made, language is a strong tool to hurt you. Okay, so in this study we focused on that. And on the other hand, the literature show how the observation of physical pain, so another person that are receiving pain, can inhibit the M1, the excitability of the primary motor cortex. This was studied through the measure of the motor potentials via single pass TMS. So in this study, we wanted to investigate whether words that has social meaning, social exclusion meaning, could modulate the activity of M1 like it is modulated for the physical pain. But we did that while the participant was viewing sequences of pain, okay, to see if there is a match between the activation of these areas during social pain and physical pain. In addition, we wanted to see the chronometric, so the temporal activation of the exclusion board. So we stimulated at different times that I will explain after. And finally, we wanted to verify our aim was to see whether individual differences in traits like empathy or self-esteem could predict the modulation of the motor activity for the social exclusion words. To do that, we stimulated 25 female students. We only selected female participants because it is well known that women has stronger empathic response compared to men. So in this case, we focused on this type of sample. These are two examples of the sequences that we used. We used 6 visual pain sequences and 6 visual functional sequences. All of the material was previously validated through a pilot study, and from this study we selected the 6 visual pain sequences that induced more pain for the participants. Okay, and subsequently we selected the visual sequences that corresponded to the pain sequence. Each sequence started with the end of the model or the object, and then a tool entered. In this case, there are cursors. Then the tool could go to the end or the object, and this third frame we call it the contact frame because the tool only enters in contact with the end of the object, but there isn't the final execution of the action. The last one, we have the pain in one case and the action in the other. Okay? And these are the adjectives that we used. We have 4 social inclusion adjectives, 4 neutrals, and 4 social exclusions. Considering that we stimulated only female students, the adjectives were in female gender. Okay, and all the material is validated. The adjectives did a different frequency, length, and they were validated in variance. This is an example of the trial. Participants were presented with the visual sequences frame by frame, and at some point, after 10 milliseconds of the third frame, the contact frame, the word, the social exclusion, neutral, or inclusion word appeared for 250 milliseconds. Then the word disappeared, and after that, in the last frame, in the pain frame, the pulse was delivered. As I said at the beginning, the pulse was delivered at 400 or 550 milliseconds from the word presentations. We stimulated the left hand one, so we recorded the MIP from the right hand. Of course, after the experimental session, the TMS session, participants underwent the Rosenberg self-esteem scale and interpersonal reactivity index questionnaires. The last one is an empathic questionnaire that has 4 subscales. The result shows a first main effect of the contest in the sense of when participants were presented with pain visual sequences, the corticospinal excitability of M1 was reduced compared to the functional sequences. This is in line with previous studies on vicarious pain, where the map amplitude was reduced when participants watched another person receiving pain. So we are in line with previous literature. And in addition, we found that such reduction negatively correlated with the personal distress. Okay, the personal distress is the feeling of distress when you are when you see another person feeling emotional distress. Okay, and in this case, it means that our participants that has that feel more distress produced a stronger reduction of the motor excitability. And it makes sense because we made everything, we manipulated all the aspects to induce that the participants was identified with the models. So if they perceive the same like they are the one they're receiving the pain, they will feel more distress. Okay, so it makes perfectly sense that where they feel strong distress, they produce a strong reaction to the pain. These are our main results. We found that in only in an early time of stimulation, it means 400 milliseconds, only in pain context, not in the functional context, social exclusion word reduced motor excitability compared to the other two conditions. Okay, so it was we predicted that when the motor system is already active for the processing of the physical pain that result in a reduction of the motor potential, the exclusion word produced a stronger inhibition. Okay, so we can say that they shared the same neural networks. In addition, we found that this reduction for social exclusion word negatively correlates, even in this case, with self-esteem. It means that participants with a higher self-esteem produce a stronger inhibition for the social exclusion, and it could be a little counterintuitive. But if we think about it, in literature we found that participants with an high self-esteem are more sensitive and reacted. They have poorer regulation when they receive a criticism or a negative feedback. So it makes sense that when participants have a strong self-esteem, they receive something like, no, I'm rejecting you, something like the exclusion, they reacted stronger at an automatic level like the MIP compared to person that has a low self-esteem. So, in conclusion, as we said, social exclusion words induce a reduction in MIP similar to the one that we observed for the physical pain. So that means that social exclusion word can reduce the mental representation of the social pain, as we saw in the physical pain. This reduction occurs in an early temporal windows and it disappears at later windows, and it's in line with previous studies, so that a stronger inhibition with language comprehension occurs within 400 milliseconds, while it disappeared after this time window, and that the modulation of M1 for social pain or for social exclusion is predicted by individual differences in self-esteem. So these results suggest an activation, as I said, of the representation of social pain during the understanding of the social exclusion meanings, and we confirm for the first time using language that social pain and physical pain share the activation of the same neural networks. These are the researchers that participated in all of the previous study that Manolo showed to you. And that's it. Thank you very much.
Some question, please. Commentary.
I have a question to Manolo. A very simple question. You study your research what happened with the negation processing when right inferior frontal gyrus is inhibited. Yes. My question is, what do you plan or think about the possibility of studying what happens if the right inferior frontal gyrus is activated instead of inhibited in the processing negation? It's only.
Yeah, the rationale is that if reducing the activation of the right frontal gyrus interferes with the processing of negation, exciting or hyperactivating this area would produce a more conspicuous effect of negation. This means, for instance, that the effect of negation for long-term memory will be greater in principle. Okay. This is the rationale.
Yes. Francesca, one question to the self-esteem. I think the results you have found is I think it's spectral in some way because very high self-esteem is not adaptable. Several studies said that the person with a high self-esteem may be rigid and very more vulnerable for this type of comment of criticism.
We expected the opposite result. I mean, with low self-esteem, more reaction to the social exclusion, because previous study, imagine study where they used the social exclusion paradigms like Sager-Ball, they found a positive correlation with self-esteem. That's why for us was a bit strange, but actually there are two completely different measures, because the Sager-Ball as a simulated situation, there is a more complex situation where you have to think what to do, what you are receiving. The MAP is really automatic and fast. We are talking about 400 milliseconds. You are not in a context of social exclusion. You're receiving a social exclusion meaning. That's why we think that, that's the main reason.
Yeah, I would like to know where exactly do you stimulate that? I missed that part.
In this
Where do you stimulate?
N1, left N1.
N1.
Yeah.
N1, you don't stimulate to the inferior frontal gyrus.
The inferior frontal gyrus was the one in the negation study.
But do you stimulate that?
No, in this study, no.
No, in the other study.
Yes,
So how are you sure you stimulate in the inferior and not in the middle?
because we used the neuronavigation system. I made a meta-analysis looking for all the coordinates from the previous imaging study, where they found during the inhibition task the activation of the inferior frontal gyrus. I selected these coordinates. I mean
Are they fixed coordinates in every subject, or you do the individual?
No, we couldn't.
So this is an issue, I believe, because for the motor cortex, it's not an issue because you stimulate and you see that it moves the fingers. But these association areas in the brain are extremely difficult to map with analysis. So the navigation system, I don't know how confident it is. I don't know, but in my mind, because I worked a lot with deep brain stimulation and with DMS, and it's what we call the pre-treatment imaging, or in surgery they do, neurosurgeons do pre-surgical planning. Basically, they take the individual that they will operate, they take all the imaging and they know where they will go. So it's planning ahead where you will stimulate. So for M1, there is no problem because you see it. And so you know you are there. But for the, especially the association, the heteromodal association areas,
No,
it's a lot of variability within the subject.
no, I mean, the most adequate protocol was to use, of course, the individual fMRI, but not always it's easy to have the access, or it was during my thesis, so I had the,
It's not just you, it's everybody.
yeah. So,
You know,
but
this is a general question, that's not just for you.
no, yeah.
Yes.
But it's actually a pretty developed protocol to use the neural navigation.
The reason I'm saying that is that this is something you can do and you can improve the entire system, because in other countries there are issues with technical issues in terms of personnel, because it needs a lot of time to do that. Or they don't have the capability from insurance companies to justify expenses for this kind of pre-treatment processes, you know, costly analysis and costly acquisition. So these are the things that I believe groups like yours can improve and have higher level publications. You know, I see it as an opportunity, not as a limitation.
Yeah.
It's everybody's limitation, but you have the opportunity to improve it.
So, question. So the next talk is Hipólito Marrero, Damián Hall, and Agustina Virba, Neurocognitive Toolbox to assess approach, avoidance, and inhibition in mental disorders, Neurocog tools.
Importante.
First of all, I would like to thank Nikos Makris as a local committee to the invitation to present our project. Me and also Agustina Virba and Damián Hall will show you the project. It's a project of translational and transference in the field of health, and it was funded funded by a competitive call, national competitive call, and we are now collecting the data. So we present firstly an introduction of the aims or characteristics of the project, and after Agustina Birba and Damian Han show you the implementation and what is the way to the project be performed in a good way.
Es lo que
Well, no Coctour is the title of the project. Analyze neurofunctional alteration of inhibitory control and approach and avoidance. Thank you. Conflict or behavioral regulation could be applied in psychology and psychiatry to assess anxiety disorder, eating disorder, or obsessive compulsive disorder. Not replace interviews or questionnaires, but try to complement them with relevant and easily accessible neurological data. And finally, the tool is trying to help professionals by artificial intelligence algorithm feeded by neurological and behavioral cognitive function data for a correct identification of mental diseases. The goals of the project are as follows. First, we need to select the cognitive tasks according to the literature of approach and avoidance conflict and inhibitory control. Second, to develop a prototype to record behavioral and brain data during performance of selected cognitive tasks in an easy way and in a short time, maybe 45 minutes at the whole. Goal 3 is evaluate or take measures of performance of preclinical samples and normotypic controls of cognitive functions taken by the cognitive previously selected task. And finally, in goal 4 is implementing a deep learning algorithm to automatically classify participants with mental disorder and controls. Our way to approach research approach is ARDO. We differentiate behavior, cognition, and brain, and we understand that by experimental paradigm tasks using by experimental psychology that indexes inhibition or behavioral regulation in approach and avoidance conflict, we can index cognitive functions as cognitive control or reward processing, and that are related to brain circuits, as is shown in the slide. Dorsofrontal sciatal circuit or orbitofrontal sciatal circuits. Questionnaire that we are using is to differentiate preclinical and normotypic participants are the obsessive compulsive inventory revised, Defoe et al., Hamilton Anxiety Rating Scale, Eating Disorders Inventory, Subversion, and the Bowies Social Anxiety Scale. Participants, as I mentioned, now we are participants are now at that moment we are collecting the data by participants, and the samples is 25 normotypic and 25 high score in obsessive compulsive anxiety, eating disorders, and social anxiety scale. One of the tasks we are selected it is shown in the slides. First, when the participant go to the lab, first they perform a resting state task, 7 minutes, and after counterbalance. By counterbalance, they were presented with go-no-go task. It's a task that's index inhibition. In this task, in this task, you can have a participant will be presented with different lights, green or red, and the more frequent. The more frequent is the green.
Arriba el puntero y
aquí el puntero.
Es una máquina de precisión.
Vale. El verde es más frecuente que el rojo. En el verde tiene que responder y en el rojo no tiene que retenerse. Excuse me. In green is go answer, and red is no go. What will happen that as green is more frequent than red, a prepotent response, an automaticized response to respond might be inhibited in order to stop the response when the red light appears, is displayed. In approach to avoidance conflict, we presented participants with happy and angry faces that are related and pro-social or no social faces, and they have a participant have to perform a movement either toward the face or against what it is indexing a conflicting situation. For example, when participants make the movement of approach a hungry face, they need to inhibit the automatic response of angry face, that is to reject, to avoid. But the movement is just the opposite, and then this is a conflict. It's behavioral regulation, what we are meaning. And finally, we also indexes this type of processes when they are semantically or linguistically mediated. For example, having tasks is a semantic tag that needs also inhibition. For example, John went to the airport to take the more close probability of more probable response plane. This is not congruent. When in order to the participants respond the incongruent condition, they need to inhibit the automatic response of plane in this case. No? And also, we try to index the approach and avoidance conflict in text, narrative, in sentences that mainly present a character and after a situation of approach or of avoidance. For example, John is a cordial or arrogant and a follow and a host or hosted John in the party, or and ignore John in the party. Well, this is my introduction. Ahora, now, Agustina Vilma to the talk.
Thank you very much, Hipólito. Like Hipólito was saying, our main goal is to develop a device that allows us to bring neuroscience into more clinical environment in a translational way. So with this objective in mind, we are trying to develop a NeuroCog2 device that is composed by two principal components. The first component is an open BCI tri-electrodes EEG, and the second component is a Dolby Air tracker. Why we choose braille electrodes instead of a classical EEG with wet electrodes is because it's quicker and easier to apply. Its compatibility with portable EEG devices which allows us to bring it to a more naturalistic environment where the patient is not stressed like in a lab environment. It reduces skin irritation and particularly is cost effective because it's cheaper than the classical EEG. The principal disadvantage of this type of equipment is that the electrodes have higher impedance. This means that the signal is more noisy than the classical EEG. But to compensate this disadvantage, we are trying to develop new pipeline analysis of preprocessing to keep all the advantage and reduce this disadvantage. Okay. So first of all, I want to we want to integrate all the data we have, the cognitive task that Hipólito was telling you, the EEG time series signal, and the tracker recordings with an open source stream layer software that is open source. The first advantage of this is really can be used in any part of the world. And it's cheaper than the classical software. And this last stream layer allows us to co-register all the signals, the EEG, the tracker, the computer signal, and it allows us, if we want to include another signal like, I don't know, skin conductance or heart rate, we can include them in our registry. First of all, we validate our setup because you know that for EEG series, time resolution is really important. So we perform a validation of our co-registration, and we send two different types of triggers. First of all, a software trigger sent to the lab stream layer from the computer, and a hardware trigger on a parallel port sent to a TMS equipment. So with this, we can compare the delay between the two types of trigger, and we found out that we have a delay of 76 milliseconds. So we correct them of all our pipeline analysis, and we are sure that our co-registration is perfectly on time. So the most important thing of this project is that we want to integrate all the information in only one artificial intelligence-based classifiers. So we have EEGs and series. We are going to reprocess them like the classical reprocessing pipeline, filtering, denoising, with independent component analysis, sharing interpolation, and segmentation. This in this first step of the project. Then in the future, we want to all of this preprocessing make it automatically, so we can generate this device that is independent of the type of preprocessing and the researcher that is doing the analysis. We are going to extract important features of the cognitive task, like reaction time and accuracy on all the cognitive tasks that Hipólito was telling you. And from the EEG, we are going to extract power spectral density, connectivity analysis, linear connectivity, non-linear connectivity, classical ERP, and time frequency. And from eye tracking, we are going to extract the pupillometry, and we are going to set this artificial intelligence-based classifier with machine learning and deep learning analysis. And we hope to be able to help psychologists and psychiatrists to classify different mental disorders. So I'll let Damian explain you the deep learning.
So the idea is to use artificial intelligence-based classifier nowadays. Even if artificial intelligence is wider than neural networks, nowadays is principally centered on the use of neural networks. The idea is to use something that mimics a neuron functioning as a central processing unit, and we have machine learning that used to use only one hidden layer. That means a connection of many kind of simulated neurons, which idea is you have an input, that's the vector that has the information from the features. You assign a weight, that's more like the dendritic part of the neurons, and that they're represented through the weights. On the soma of the neurons, we have a function that makes the integration of the information that comes on the input, and it produces an output that is represented by the Y. So the connection of many kind of neurons make a neural network. When it has only one layer, is named machine learning, and all the algorithms already developed in the past, even if it's go-ons, used to have only one neural network. But the big advance and the big achievements that nowadays have the artificial intelligence is through the use of deep learning. That means to have many different layers of neural networks with different kind of functions in the integration functions of the neurons. So this kind of approach gave place to different kind of goals in order to classify or predict some results from input functions. This is the idea we are using, the supervised layer, supervised learning. The main idea is we have something that is represented the input. This is the features of, for instance, on this image, a cat image, is represented on the features by the red, green, blue of each pixel of the image. All this information is transformed to a vector that keeps the information of the red, the green, the blue, and this is the kind of vector on the input layer. And we know that it's a cat, so we assign to the output layer an expected value represented by the Y. 1 means that it's a cat, 0 means it's not a cat. So on the neural network, there is a loop on the forward pass. We adjust the weights randomly at beginning, and we obtain a Y prime value as results. we calculate the distance between the y prime we obtain with the y we know is exactly the value expected, and we loop adjusting the weights of the neural network in order to train the network to recognize exactly what we presented. So in the future, once the neural network is trained, once we present an image of a cat, it automatically says it's a cat. And if it's not, it's not. So the idea is to have a device already trained with the data that comes from all the features we will extract from the EEG and the task and the eye tracking we are using on our device. There is a big amount of neural networks, kinds with different kinds. We choose to test on the area of machine learning. The linear regression is the baseline, is the most basic one. Support vector machine is a machine learning efficient model. And on deep learning, we use mainly the multi-layer perceptron. That's the most classical one. It's connect everything with everything. Then historically, the convolutional neural network was developed mimicking the visual cortex on the brain. And in order to grasp information when we are dealing with sequential data like time series, they developed another kind of neural network that is termed long short-term memory and is focused just on time series. And the last one is what is actually the most important one is the new area of the transformers that are concentrated or focused on having the capability of attention and focusing on key factors. So our goal is to have an X that comes from different possible features obtained through the ERP, time frequency to velocity, response time from, as Agustina told on the idea of that will nurture our neural network as X on the information that came into the neural network. We are going to try different kind of neural networks, and we expect to obtain as output a classifying on the disorders that already told Hipólito for this neural tool. Our last goal is also to provide a kind of evaluation. That means as we got all the information through the task of response time, through the pre-processing of the ERP, for instance, and N2, P3, and 400, all this kind of information is related to the cognitive approach. So, as we have a population of control people that represent the normal way of acting, so we expect to have different values, normal values for all, obtained from all the cognitive tasks. And when some new participant came to test the device not only will provide classifying, that means if it has or not one of these kind of disorder, it will also give some information if this participant, for instance, John Smith, is over the mean or below the mean on any of the data obtained through the cognitive approach of the task we applied. So that's the global idea of the Neurocode 2, and it will be theoretically, if it works well, applied on, for instance, on primary health facilities. So that's all.
Thank you to the team.
And that's all the team. Yes.
questions, please?
Yes.
How many diseases are you targeting with your running these battery of tests and
At the moment, the idea of the project are only for disorders, not diseases, but mainly disorders. That's alimentary disorder, or obsessive compulsive disorder, anxiety, social anxiety, and general anxiety. That's the four.
Do you have an idea of how many persons you would need to join the classifier?
We are planning. We are going to have 25 controls, generic controls, not having any disorder, and 25 for each disorder, specifically for each disorder. Even if there are many comorbidities, we expect to have 25 for each disorder. So an total amount of 50, that is more or less .05 for the G power of the project.
Very interesting.
So the question. I have a question about because this is a project of concept. Yeah. And I suppose the final objective of this kind of project is the applicability to and translation to the national system of health. So the question is, in which measure this amount of measure of different levels, physiological, ERP, eye movement, cognitive tests, etc., could be implemented in the national system of health, given the time of consumer to pass to a patient. This system could be very important.
Well, as a proof of concept, the idea is we have more or less 1 hour to pass all the tasks. But once we arrive to the final conclusions, maybe, for instance, for classifying, it's enough the resting state. We don't need the other tasks. So one possibility is we pass, for instance, 5 minutes of resting state if it arrives to tell us that there is a disorder or there is not a disorder. That means first filter. And then you can, well, there is a disorder, let's pass the other task. That means half an hour more, or it depends on that's the protocol that could be applied on first care, let's say. So the idea is not to start with 1 hour for each people, but maybe, but we need to adjust. Even that's a proof of concept. So the idea is we start with that. If we start with 25 people, and once the neural network is trained, if it works well, it's okay. If we need more improvement, we can get more people, and more specifically, people that already is not selected from the questionnaires, that is the case just now. But for instance, we have an agreement with the hospital. They can send us people that is already under supervision for this kind of disorders. So first we need to pass the proof of concept. Then we need to improve the device and the possibility.
To optimize.
Only to complement the intervention of Tania. The result of the project, you can help systems. It is possible that we try. It's a transfer project. We contact with the enterprise and public organisms in order to present the result of the project. But you can find the more easy, that is, for example, as Damian told, to know to classify by the present state very quickly in 7 minutes if the person is such type of disease. But the project is oriented in the framework of ARCOS. What that means is that we try to evaluate inhibition and behavior regulation functions, and that could be perturbed in different ways in the disease we are evaluating now, and we expect that health services are also interested in evaluation, in using evaluation. What not only this person is talk or make or is did, excuse me, or even that in general anxiety disorder are have a retinal state that clearly identify this type of disease in general. But it's so important that professionals have knowledge and information about what type of functions are perturbed in general and in each of these diseases differentially. But we don't know because, as you said, health public system. Stefan also thought that usually is not interested in something so complicated in the normal professional activity. But this is not our problem. Our responsibility is to present results and to offer improvements in the health service.
Yeah, of course. If I may, I think the problem is that all the transformation you have to do to the seniors, to get the N for 300 and B for 400 and so the connectivity matrix. That's something you have to do. That has to do with you have to do manually because sometimes not so easy to do with the program. So all these things you have to do it before you fed up to the classifier, and that's something that is very difficult to do in a public service. You need to have this kind of outsourced, or you need to have some researcher or something which is well trained doing these things. It's not like a radiologist that produces the images and says there is a tumor, there is so it's not so easy. And also, in my experience, the problem with the physicians is that they don't understand what the program is, the tool is looking at, and then they are distracted because with a very deep learning, you can get a very high classification accuracy. But what is the program looking at? Sometimes it's difficult to say because they do this high nonlinear transformation to look at the features. So what is the program looking at? They say this is food disorder and not OCD. It's difficult to answer. And then the doctors, they are very trustful of this kind of black box approach. I mean, so that's why it's so difficult sometimes to go from basic neuroscience and machine learning approaches to clinical neuroscience, because there's a gap. It's sometimes difficult to fit. But it's a very nice idea. I like it. It's a good approach. Problem is that then you have to talk to the doctor. And someone has to create these connectivity matrices and then I mean, it would be wonderful if you just put the EEG and then you create everything, but you do that everything is done by the machine. Then that would be nice, but of course, I mean, so far it's not so easy to do it everything automatically.
So, do you think that they have some devices and technologies that are some black box and this, and
but they're used to that.
Cardiologists use horses, and the horses analyze the heart signal 24 hours and obtain statistical patterns and compare them with some.
But then again, they can understand what is there. It's high radioactivity. They say, okay, they have this time between intervals on some. I mean, first moment, second order moments of the distribution. Connectivity matters because you have to explain. I will talk a little bit now, but you have to explain what is that. And the moment you talk about new information, but it's a good approach, and somehow at some point you have to find a way to talk to them because one way or another, there's a lot of information you are not extracting, and you need it, and it's very useful. All these methodologies, remember when we were in China, that they were already using this as a eye to the diagnosis. Because, I mean, they don't ask the doctor, they don't ask the patient. We are doing that because we are the government, and you have to do it because it's just, I mean, you cannot do that in Europe, but somehow it's the way to go, because otherwise there is a lot of information we are not using and they will be beneficial. So also, I guess for the first time they use an MRI and say, okay, how is this speed producing this complicated magnetic field? But now everyone is going, okay, let's go to the MRI and see what is going on there. So I think with time,
It takes a time.
yeah, it takes time, but
we have to.
I mean, if the technology is good, I think
Yeah.
it's, eventually
I agree.
it will enter into the system. But you need some patience when you talk to the doctor.
Yeah. Now,
Okay.
that we are.
Okay, one else before José Luis y Nico fueron a poner unos bocadillos para que la gente no muera de hambre. Entonces, bueno, tenemos algo para comer. Y ahora, now,
Yes, yeah. No.
give a talk of Ernesto Pereda, who's called connectivity in the study of Alzheimer's disease, pros, challenge, and the way forward.
Thank you. Okay, thank you. Okay, so thank you very much. Thank you for the invitation. It's almost complicated to do the last one because everyone is waiting to finish for a very interesting course. And I was not very sure about the audience, so I tried to make it a little bit didactic and explain quite simple things at the beginning. So I hope it is not too more for you, but hopefully, in any case, it will be like a good reminder of what we are looking at. So this is a brief overview of what we are going to do. We are going to explain what is the magnetoencephalography and EEG from the basic principles of the signal we finally measure. We review what we can look at, what is connectivity, and how can we look at that from magnetoencephalography and EEG, what is the pros and cons. We will explain an application to study for Alzheimer's disease, which is the one in which I have the most experience working with colleagues from the University de Madrid, a group from Fernando Maestro. And I will make some suggestions for how we can proceed further in the field and what should be the way forward and some conclusions. So, I mean, I know this is very basic, but what we are looking at in the synapse. Okay, so we have the presynaptic potential that travels through the axon. It's very fast and can be electrically modeled as a quadrupole. And we have the postsynaptic potential, which is far in the dendrite. It's slower and it's modeled as a diagram. Okay, that's the basic thing. And any of you that has been working now a little bit in the field, I guess, already know these things. We have here this intracellular current here, and they produce two effects. One of them is an extracellular pulse current or return current. That's the one which is going to be measured by the EEG, different in the electrical potential between these extracellular volume correction and current, and also magnetic field, which is perpendicular to this return current, and that will be the one who will be measured by the magnet. So this is a schematic representation, and so we see that both modalities, they basically see the same effect. Only thing that the EEG detects the secondary currents, one currents outside the extracellular one, and MEG detects the magnetic field associated to such currents. Okay. The problem is that a single neuron is of course not enough, because we need the contribution of many neurons that also have to fulfill two conditions. That we we need to have spatial summation. All currents should be oriented in the same direction. And also temporal summation in all the currents should occur simultaneously. It's a representation here of the neurons in the cortex and how they produce the volume currents and the field. Temporal summation, which is one of the conditions we have to fulfill, is much easily happens much easily for the postsynaptic potential, which are slower, and not for the presynaptic ones. So the largest contribution to the magnetoencephalography and EEG would be the currents flowing through the postsynaptic, either inhibitory or excitatory postsynaptic potentials. As for the spatial summation, you will know that back even 1905, when we have these beautiful drawings from Ramon y Cajal. In the layer 5 of the cortex, we have these beautiful neurons called pyramidal neurons that have an apical dendrite oriented perpendicular to the surface of the cortex, and all of them are quite nicely aligned. They are right reducing the necessary spatial summation that allows us to record the EEG and the MEG hysterocrania. I mean, if the organization of the cortex were different, then it won't be possible to get or to measure this activity outside the skull. So we are, in a way, we are lucky. We need approximately 10 to the 5 neurons, which is probably a patch of 1 square millimeter, aligning in parallel and firing simultaneously pyramidal networks in the cortex, something like that. And for that, we will have this current density, which is around 10 to the minus 9 nanoamperes, and producing a magnetic field of 100 femtotesla, which is actually very small. This is the different levels at which we can look at the information of the brain, or the different levels at which we can look at the brain. This is the molecular one, even a complete description of the neural functioning, that is way outside our scope. Several level circuits and the brain areas, and which we can try to look at correlation between the activity of the different areas at the area level. Okay, that's the one in which MEG and EEG works. One important thing to take into account is that pyramidal networks are located in the gray matter. So in order to reach the sensor, we have to go through different tissues. First is the white matter, the gray matter itself, the cerebrospinal fluid, the bone, and the skin. The thing is that the way in which a magnetic field goes through all these tissues to the skull, and the electric field goes as well to the skull, is a little bit different. Magnetic field goes through tissues which have all of them the same magnetic permeability, which means that the magnetic field goes almost undistorted from the way from the place in which it is created to the place where we measure it. However, in the case of EEG, the tissues have very different conductivity, especially the bone is terrible. Secondary currents are directed and changing from one type of tissue to another, and it means that the activity created by the gray matter here is quite dispersed in different parts of the skull, which is this distortion creates that one single source of electrical activity can be picked up by different electrons here. So creating something which is called the volume convolution problem. So I mean, as a result, it's much easier to know where does the MEG signal come from as compared to EEG, and if we want to make localization of brain sources, MEG will be always superior, right? If you compare MEG with fMRI, the good thing about MEG or EEG is the direct measure of neural activity, postsynaptic currents. They have excellent temporal resolution, which allows the study of dynamic cognitive processes, and is minimally invasive. And if we compare MEG and EEG, in the case of MEG, we have less distortion of the signal, which makes it a little bit superior. It has better signal to noise ratio, and especially is less artifact for high frequencies. Also better spatial resolution, but it's not always bad news for EEG because EEG is more sensible to deep sources, and also it's important that we see radial and tangential sources. And tangential sources in the circuit, they are only seen by the EEG because the MEG, if you look at the MEG, only the tangential, MEG only see tangential ones, but not the radial ones. Okay? So they are more or less, I mean, they are very similar, but somehow we can try to get the information of both at the same time, which is has been done in the past, and we have now applied for a project to the ministry and try to find the way in which EEG can be measured to get as much information as possible to get close to the MEG, and hopefully we can have a little bit of research on this field for the next years. But it is also superior to fMRI in everything, I would say, except the good localization of the activity. Also, if we have sufficiently precise anatomical information, we can try to build a model of the current and magnetic field propagation, and by inverting this model, which is called the inverse problem, estimate the origin of the signals measured in the model is normally the MRI of the subject, but something place can be also used. So a typical preprocessing will consist of recording the activity, in this case with the MEG and the filter, automatically reject artifacts. You can also band fast filtering in the classical bands. And then you solve the inverse problem using the MRI information. You do the correlation between the MRI and the MEG or the EEG. You create a bond conduction by knowing which of the sources are projected to each of the sensors, and you solve the inverse problem and create an approximate model of the activity of each source, maybe in the cortex from the data you get from the sensor or the ELF. Okay. And then, of course, you can analyze the signal. You can do it univariate analysis, focusing in the study of the activity recorded by one single channel or source, like ERP, ERF, or time frequency representation. That was like kind of classical way of doing things, but now I think with the last 25 years or so, functional connectivity field started, and it implies to work in B or typically multivariate ways, so that we have to analyze the relationship between the signals we will record at two different places, or the sources we reconstruct from this signal. The problem is that we can't measure, I mean, we don't know whether the signals are actually correlated, and we have to look at this statistically to try to understand if the corresponding sources are talking to each other. That would be an example of this, how this can be done. If we have two different sources and we look at same times, we try to find some kind of similarities between the patterns at the same times, and then if we look here, we see that at similar times we have similar pattern in both signals, and this can be quantified to understand whether this is below above what would be expected by chance, and in this case we can put in a number there and say, okay, these two sources here are some way talking to each other, right? If we do it for all the possible sensor sources, we have this kind of connectivity matrix, which is very nice. And got all the information about which areas are talking to each one based on the statistical dependency between any of the characteristics of the corresponding signal we have recorded, right? Of course, we can do it at the sensor level by looking at the signal and the 3D or the 2D representation. The problem, especially with the EEG, is this volume conduction effect I told you about. The signal is distorted, so we have one single source picked up by different electrodes, and if we look at this statistically, that will be regarded by the index as a kind of connection between the two electrodes, two sensors, which is actually not happening. It's just an artifact of the way we have to measure the signal. So it's always good to have the tooth reconstruction and look at the different areas, but inside the brain. But there is a problem that we will talk about later, and how we group all these nodes to create our brain areas or region of interest. We can use something like the Brodmann areas or different atlases, but it is sometimes not very easy how to go from, suppose, one area that has I don't know, 10 or 20 different sources, how to produce the representative time series for this area. Is not kind of a simple problem. Okay? Well, while we have done all of this, we have now a bunch of methods we can use to look at the connectivity. We can use classical methods like coherence that are very well understood, or correlation that only look at the power or the amplitude of the data. But we can also look at the phase of the signal by first doing filtering and look at a specific band. We can look at zero-lag correlation or correlation with some delay, which allows us to infer directionality in the measuring. We can look at the broadband signal. That's something that is typically not done, but it's, to my mind, very useful, because in case we have linear connectivity, we cannot look at linear connectivity by looking only at a portion of the signal by filtering with the phase synchronization. So looking at the whole signal in a more comprehensive way using this kind of index, it's a little better than using this or that method. And we can also look at directionality by doing prediction of the signal with linear modeling, and also look at using the informatic theoretic measures. So we have like a big bunch of tools that we can use for synchronization analysis. The problem is that in all the comparative analysis done so far, including some one of our own, none of the measure is superior to the other one, and it pretty much depends on the application you want to. Right? For instance, this is the, I would say, the most typically used, and not because it's very powerful, but because it gives you information in the frequency domain, and it is easier to compare information in the frequency domain with previous literature. So you can say there is a coupling in this band or that band, and because you already know very well what is happening in each of the bands. But you have to understand that the way and the reason why people normally filter the signal is because in the tools we have Fourier transform filtering was very simple, but we can work also at the level of the full signal. So which one to use? I mean, how to choose one? It's always a complicated problem, right? In any case, the analysis will be as such. We will have the Bilbul channels reconstructed using the inverse method. Oh, I think it's going on. Okay, minutes. It's too short time. I'm trying to go fast and not so fast. And then you calculate. You have the matrix. You can have one for each frequency band, and of course you have to suppose two group of subjects with the different roles and the different matrices. You make the statistics and you say, okay, there are differences between the two groups for this frequency at the region of that region. I mean, statistics a little bit not as simple as doing a t-test, because we have many operations, but it's something that you can handle and it's work. I will show you an example of collaborative project we carried out with Madrid and Cambridge. Analyzing data from people with Alzheimer's disease at two different stages of the disease. You possibly know very well Alzheimer's disease better than me. It's responsible of 60 to 70% of the dementia cases. It was described 120 years ago, more or less, by Alois Alzheimer. And it's characterized by neurodegeneration, tangles, and amyloid plaques. I will quickly explain this thing in the next slide. Brain atrophy and symptoms, typical symptoms, and cognitive deficit in memory impairment. So this is a neuron. You have amyloid beta, which is a fragment of a large protein found in healthy nerve cells. It's associated with the metabolism of the fat in the brain. The problem is that in Alzheimer's disease, these molecules clump together into plaques outside the neuron, and these plaques has a toxic effect. So the neurons start to die, especially cholinergic neurons, they start to die up to 70% of the neurons. This is one of the effects or one of the problems that we find in the Alzheimer's. And the other one is another protein. This one is a protein inside the neuron, which is called tau, which helps to maintain the structure and stability of the microtubes that fed the nutrients and other matter around the neuron. This protein also breaks down and proteins start not working, and as a result, tau forms also tangles, but also microtubes break down. And eventually, without any way of transporting nutrients inside the neuron also eventually dies. So it's like there are two mechanisms, the problem with accumulation of beta-amyloid plaques and also the tau. Interestingly, this Monday, I don't know if any of you have seen this news. They reported in Nature Medicine that 5 patients who were 40 years ago transplanted with hormones, human growing hormones from the pineal gland of persons who had later on developed Alzheimer, also developed Alzheimer without any genetic risk. So it seems that it is not just as simple as that, and that there is also something that can happen in all parts of the brain. In this case, with this finding, it is just one single report doing for a group of University College, but that will be also interesting to look at because this is the classical mechanism involved, but it seems that the things are not so easy. Okay, so the thing is, what is important to look at the neurophysiological data in the Alzheimer, because the neuropathological process normally starts before the cognitive symptoms. So if this is the kind of the detection threshold, you have cognitive impairment is here, but there are also some mechanisms taking place before the subject already has symptoms. So we have typically 3 stages. The symptomatic stage, the subjective memory complaint, cognitive impairment, and the Alzheimer's. This is I think you have also seen this one. A painter named William Hunter Holland did some self-portraits in the progression of the Alzheimer's disease, and you see how the perception changes along the continuum of the disease. The first aspect will be the position of an amyloid PET. This can only be detected by PET. It doesn't make sense to make a PET to anyone you suspect that is having Alzheimer, so it's not very helpful. Then you have the synaptic dysfunction that you can look at specialized PET and fMRI. The brain structure is MRI, cognition with a neurophysiological exam. But the idea is to look at the synaptic dysfunction by doing magnetoencephalography or electroencephalography, which are non-invasive and relatively easy to apply, and non-invasive and even easier to do that. Which products we can find in the subject? Maladaptations such as diaschesis. This is dysfunction in remote regions, so we have lesion in one part of the brain, but the dysfunction is placed in another part of the brain because they are connected, so it makes sense to look at connectivity. You can also have transneural degeneration, so the degeneration starts in one part, and because of the connection between the different areas, first the entorhinal cortex, then this degeneration goes through a typical line. And then also you can differentiate the differentiation, the segregated non-specialized activity. And you can also find adaptation in which there are other systems that assume the function that is necessary to carry out by the brain and is not longer performed by the area that is being damaged. Okay, so in all these cases, as you see, it makes sense to look at connectivity because it's not just one area which is not working well, but the connection between the areas which is working in a different way as to compare to contours. So I'm going to describe quickly the results of project we did in the framework of the Joint Program for Neurodegenerative Diseases of the European Union. It was a multi-center study between Cambridge and Madrid. In this case, it was Center for Biomedical Technology. Now it's University Complutense de Madrid, and the Medical Center in Cambridge. And we have two different groups, controls and MCIs, by cognitive impairment. You can find the details in the page. We have a total of 134 subjects, 70 controls, 64 MCIs, more or less balanced in terms of sex, age, and with a big difference, of course, in the mental state. As you know, this is much higher for the control subject as compared to the MCI or the Alzheimer's. We perform spectral analysis between 2 and 45 Hz. I'm not going to say the details, it doesn't make sense. And we apply a battery of connectivity measures, looking at phase and the signal as a whole, also looking at zero phase correlation and non-zero phase correlation, and phase transfer entropy that also allows you to look at the directionality. We use two different ways of looking at the representative signal of one of the ROIs by taking the center voxel of the PCI, and also two different atlases, the AAL and the Harbor-Oxley, which are one of the two most used atlas in the literature. Well, I mean, with any of the two atlases, we have significant difference between groups with different measures. And also we apply very simple machine learning classification, taking first only the power, only the connectivity, only the millimeter state, and or combining all of them to try to make the best possible model. It's important with our sample size, even for a binary classification. Most people say that the chance level is 50%. It's not done like that. I mean, if you have more than 50, sufficient, if you don't have an infinite number of subjects, the sample is shorter, you can have, by chance, a larger classification accuracy than a 50%, and actually for this number of subjects we have, 63 is the threshold. Everything below 63 won't be different from chance. If you just make a classification by comparing the two centers, it seems that we cannot differentiate both centers, so it's a good result, because the MEG machines were the same one, MRIs were very similar as well, so we cannot distinguish between the two centers. This is good, so we can pull all the data together. That's kind of a sanity check. If we do a classification with power, we go only marginally better than the chance, 70%, which is only correctly classifying 7 out of the 10 subjects, which is not too much. This is a vision matrix and the ROC curve. This is another way of reporting the data, but it's basically the same, right? You have 30% of wrong of errors. What happens if we use functional connectivity? That's more or less how they look like. For both centers, we have clear differences between control and MCI. Whereas for the same center, for different centers, the same group, there are no differences, so it's okay. If we look at that, we look at this whole signal, mutual information. Again, we are close to chance and close to what we got with the power alone, so not much improvement. If we go again for another one, which is the directional information of phase connectivity in the beta band, again, we are not very high above the threshold. But if we look at our subnetworks and we take even if we take only mutual information, we are able to improve our model the accuracy by taking not only one of the subnetwork, but different subnetwork at the same time, so including more features. Okay, let's do it. But we can get even best classified if we use power, functional connectivity, and then neurophysiological. So it's quite related to the things you are doing because we have multivariate measures, functional connectivity, and neurophysiological. And if we add all this information, we get up to around 83% of accuracy. So it seems that information provided by any of the measure alone is not too much. I mean, it's not very, it's not enough to classify. But if we add up all the information and select the features by doing a proper feature selection algorithm, like in this case was very simple PCA using all the data, then combining the three modalities, we can get relatively decent classification accuracy, right? So in our case, the best classified was a combination of power spectra, different functional connectivity index, broadband and band specific, and the metal state. So we believe that MEG or EEG can be a potentially good non-invasive biomarker in this case, and in any other cases by combining information of univariate, multivariate, and neurophysiology. So what would be the way forward? One problem, which is typical, is that we have these many sources, and then we group these sources into different regions of interest. The problem is that the way in which we select the representative time series for each of the regions based on the sources they each of the region contains clearly affects the result. So if we take the centroids of only one time series of the sources, we got this one. If we got the PCA, we got this one. If we got the mean average value of the PLB or any other connectivity indices within all the possible pair of sources, we have this one. Of course, there are similarities, but they are not exactly the same. So it would be nice. It would be nice if we could instead use a different approach. That would be taking all the sources within one of the regions and do a multivariate analysis. That is a little bit more complicated, but can be done. There are measures like multivariate looking value or distant covariance that can be used for that. We are doing this type of research right now and comparing this multivariate analysis with the different approaches, taking one single time series, trying to understand which one represents best the information contained in all the. This is a little bit more complicated in terms of methodological, but it's very interesting. Another thing that we can do is the dynamic information. Even if you have an ERP, you calculate the average year information of the ERP. I mean, ERPs are quickly changing data, while calculating only one value for the whole ERP, instead of taking advantage of a sliding window of reduced size and the fact that you have a lot of information because you have a lot of trials. You can use these small windows and use this information to produce, which is called into trial phase coherence. It's an index of correlation or phase synchronization that can be provided with temporal information. So we can also have an idea of the dynamics of the differences. Why it's important to do it like that and not in resting state? Because, I mean, even from the point of view of engineer, it is normally that if you have a disease, differences with control should be greater when the brain is stressed during the cognitive task. And these differences might not be as clear in the resting state. Another interesting thing is looking at the relationship between functional connectivity and structural connectivity that you can get using DTI. DTI is like the roads, and functional connectivity like the cars going through the roads. In a healthy brain, one expects that the difference between the structural and functional connectivity could be relatively large or important in those cases where we have a flexible brain that can create connections using indirect paths. But if we have disease or someone who's already through the pathological road, then the brain lacks flexibility, and you have something like the structural connectivity here. It's very similar to the functional connectivity. So differences between structure and connectivity might be a sign of degeneration, right? You have bigger differences because you have more healthy, flexible brain. But for me, the most important thing that we can do is try to model the brain. This is, I think, the most ambitious way to try to understand what these differences we are reporting actually means. And this is an example of an interest paper published in 2017, showing that you can try to, in a way, reduce the differences between healthy controls and MCI patients by changing the neural stability of the cortex, the excitation inhibition balance. And this can be done if you create a model of the brain in which you can control such parameters. And this is called a digital twin, a model in which you can intervene by changing, I don't know, connectivity of the channel, the excitatory currents, regulatory currents, and you see what happens to the model when you change this parameter. Try to take the model as close as possible to the healthy brain, and then you can design an intervention by, for example, applying TDCS, reducing connectivity, excitability in this part, increasing excitability in the other one, trying to take your network as close as possible to the healthy brain. This actually way of working can be applied to any other situation in which you want to take the brain from one point to another. That's very interesting. So what would be the conclusion? Estimation of brain sources, we think is an important step toward improving MEX because it gives scalability as a biomarker and also minimize intercenter variability if we want to, in the case of Alzheimer's disease, growing larger studies. And the source space are easy to interpret, of course, than sensor spaces. Of course, this also adds some steps in the preprocessing pipeline, which need additional modalities like MRI and also additional indices. So there are a lot of degrees of freedom, a lot of decisions you have to take, and this also makes the replicability suffers. As for the conclusion of MEC functional connectivity, we can say that brain functional connectivity at a more or less industrial scale, so to say, is a now well-established research field, has been there for more than 25 years. It has evolved from the study of the bivariate correlation between two channels at the sensor level to analyze multiple regions of interest at the source level with more sophisticated methods. And many indices and statistical methods are now available, but there are still with some road to go, right? So if we combine these methods with machine learning or artificial intelligence methods and brain modeling, which I think is also very important, we believe that functional connectivity from MEC or EEG might play an increasingly important role, not only in basic neuroscience, but also in clinical practice, which will help us to better understand and diagnose different diseases. I would like to thank the group of Fernando Maestu. You can see also one here. And some of the people that has worked with me along the years. Ricardo did the PhD with me, also Juan, Sandra, and Pablo was Juan de la Cierva researcher here, and they are is now at the University Complutense, also at the University Complutense. I don't know exactly where Sandra is, and we have Juan here that has been a brilliant career as a postdoc in Harvard. So it's a very nice group, and I have been pleasure to work with them in the last years and having access to this very good quality data, and also the network collaboration that has allowed me to look a little bit more into this fascinating field of magnetic and electroencephalography research. Thank you very
much. Yeah, thanks. Very nice. Wondering about this first point you mentioned, that is one of the ways forward, about averaging how to combine signals within ROIs.
Yeah.
Yeah. So isn't the problem just because you're using ROIs? Shouldn't you just take these sources as as the data-driven locations that way we're interested in?
Yeah, I mean, in MRI, you can't do it because you're getting the signal more or less voxel-wise, but you have to take into account that with MEG and EEG, the most signal you have to, the most independent signal you might have is the number of channels you record. I mean, typically it's around 100. So how can you go from 100 channel or sensor you record to 1,000 channels? I mean, 1,000 sources. Doesn't make much sense, right? I mean, in principle, they are not completely independent. So in principle, of course, you can work with all of these. But the problem then is that you have so many possible combinations that any effect you have is strongly reduced in terms of your ability of detecting it, right? And also, I mean, what we are trying to do is something in between. We accept that we need to have the ROIs because they are meaningfully or anatomically or functionally meaningful. And but then why not taking all the information that we have by taking all the sources within each ROI and calculate the index of connectivity, not one to one, but all to all. Right? This is mathematically a little bit more complicated, but it can be done. That's what I think. I think there's one paper from the Hansen group in Cambridge with this distant covariance, but somehow they didn't pursue this idea because it's a little bit slow to calculate and it's not so easy to interpret. But we are working on that because mathematically they have, especially in the statistic field, they have developed this idea further, and we can also, if we have, suppose P sources here, Q sources here of a length n, we might have an estimation of what is the statistical significance of the value we have by applying some of the new results in the field. So that will be interesting because we can also compare when we use all the information and when we use one representative time series and see which of the representative time series is closer to the information you can get if you perform all-to-all calculations.
So the question. Only Ernesto was just a question that is products of my ignorance about techniques only. I never understood why the MEG is a technique that allows a high resolution in localization of source, for example.
Yeah.
And EEG is not such a. Is the question of noise? I don't know.
Well,
the signal is
noise is one, but the main problem is the way in which, because they are measuring. If you can go to the, it's one of the first ones. Yeah. Go. No. Yeah, this one. This one is perfect. Yeah. You see, this is what MEG is looking at. It's the magnetic field generated by the intracellular current. This magnetic field goes completely undiscovered from the gray matter to the scalp because all the tissues you have to go through, they have more or less the same magnetic susceptibility, right? But they have different electric susceptibility. I mean, one interesting example is what happens when you put a pencil into the water. You see that it looks like the pencil somehow has bent because there's a difference in the diffraction index. So the information you get about how the pencil is there is actually not quite right, and you're getting wrong information only because they have the air and the water, they have different diffraction index. This is actually the same thing that we have because sorry. No. Number, I think it's number 9, something like that. No, more. 11, 12. Yeah, 12. Yeah. You see, you have white matter, gray matter, cerebrospinal fluid, bone, and skin. The magnetic field goes completely undisturbed, but the electric field, because of this difference in electric conductivity, it goes distorted, which means that if you have the extracellular current here, the electrical activity is changing, and also this extracellular activity there is seen here and here.
Okay. Yeah.
It's like because of the way the extracellular current information is transmitted through the brain. I mean, if you go to intracranial EEG, that would be better. But of course, you cannot do it normally. I mean, this is you're doing some surgery. The good thing about the MEC is that they can pick up the information quite localized because the magnetic field is more or less understood. One is, of course, that it is very expensive.
Thank you very much. Pues, terminamos aquí el seminario del UNED. Es una muestra de lo que estamos haciendo. Son solo cuatro integrantes del instituto, pero muy representativos de lo que estamos haciendo en los campos, ¿no? No solo de la investigación básica en neuroimagen, sino de los proyectos de transferencia. Y para nosotros es muy importante mostrar esto hacia afuera también, ¿no? Y estamos colaborando con diferentes universidades de todo el mundo. Y nuestra capacidad de internacionalización no solo de atraer gente está incrementándose, esto nos va a dar más poder. Estamos atrayendo a personas, a investigadores con las calls, con las convocatorias internacionales y nacionales que hay. Esperamos hacernos más fuerte. Hemos enviado gente a otras universidades también, investigadores que se han formado con nosotros. Están en centros de primera fila, por ejemplo, Swan también, por ejemplo, ¿no? Pero hay gente en Oxford, hay gente en otros pueblos de Europa y de Estados Unidos. Y esperamos que esta muestra de lo que hacemos sea también representativa de lo que hacen todos los investigadores, más de 50 personas asociadas al instituto, del cual son también miembros honorarios Nico Martins y Stefan Palandi, aquí presente, y también Panteris, todos ellos miembros honorarios del UNED, ¿no? Esperamos que todo esto nos fortalezca y nos haga más competitivos. Gracias a todos. Ahora tenemos el pequeño lunch y después tenemos la charla de Stefano Palandi, sobre que empieza esta serie de conferencias sobre gambling y otras conductas adictivas en el marco también del alcohol, que es muy interesante. O sea que como quieras. Gracias a Luis Carrizo por la conferencia.